With this video, we'll have a look at the reciprocal circular functions. And we'll start with the cosecant function, shortened to cosec. Okay, so cosec x, which is just 1 over sine x, and a plot of it you can see here. How we arrive at this plot, or later on how would we sketch them, I'll have a look in further after I introduce the three reciprocal functions. But for starters, it's shortened to cosec, so we want to find cosec x. The plot of that is shown, y equals cosec x, and it is actually written cosecant. Okay, so just be aware, cosecant. Okay, now you notice there's these vertical lines here, the asymptotes. That tells you something about the domain. Those points pi, 2 pi, 3 pi, minus pi, and so on are not included. So the domain is all the reals except for the set of points x such that x equals pi times n, where n belongs to the integers. What may not be clear from the plot here is that the range is the reals excluding the open interval -1 to 1. And when we come to sketching them, we'll see later on why that is. Because this is really just, you can plot cosec x from simply sine x and then take the reciprocal of each of the values of sine x, and you'll end up with this graph, and I'll show you that later. The first thing, let's just introduce them with the domain and range. Okay. Next one, we want to have a look at secant x, or sec x for short, and that is just secant. Secant x, which is just 1 over cos x. And can I just come back here a little bit? There was something I did forget to mention. How did we get this pi times n? Well, if you look at sine x, you know that sine x is 0 at x equals 0, x equals pi, x equals 2 pi. And so when you take the reciprocal of 0, it's undefined. And so that's how the asymptotes. So this graph, this plot here, the graph of y equals cosec x, asymptotically approaches those values but never actually reaches them. So they are undefined at the points pi, 2 pi, 3 pi, minus pi, and so on. Okay, the function asymptotically approaches those values but never actually reaches them. They're not defined at those functions. The function is undefined at those points. Okay, let's come back now to sec x, or secant x. Same thing again. Think of the graph of 1 on cos x. You know that cos x is 0 at pi on 2, 3 pi on 2, and so on. Okay, so we just need to look at that 5 pi on 2 is another one, and then going back the other way, minus pi on 2. And so wherever cos x is 0, the function secant x is undefined at that point. And so the domain is the reals excluding the set of points x such that x equals pi on 2 plus pi n, where n belongs to the integers. So you can see that for n equals 0, first asymptote pi on 2, minus pi on 2. And then n equals 1, you're going to have 3 pi on 2, and so on. Okay, the range for this again is the reals excluding the open interval -1 to 1, and we'll see that in the plotting. So that little gap which is sort of present there, it's visible there, you can see there's a little bit of a gap. Because cos x oscillates between +1 and -1, the range of cos x is from -1 to +1, including the endpoints. And so when you take the reciprocal of those, that's how you're getting your graph here, your graph of the secant x. Let's have a look at cotangent x. All right, so that is cotangent, okay, or cot x for short, and that's simply cos x on sine x, which is 1 on tan x. It's the reciprocal of tan x, so it's cos x on sine x. And again, where sine x is 0, clearly this cot x is undefined. And so that occurs for, again, the n times pi. So 0, pi, 2 pi, 3 pi, and then the negatives of all of those. So the domain becomes the reals excluding the set of points x such that x equals pi times n, where n belongs to the integers. As you can see, the range is all the reals. Okay, so there we go, a brief introduction to that. Now, just basically some symmetry properties here and some other trigonometric identities. Cot of pi minus x is minus cot x. Again, you could work that out using cos x over sin x, as I did in a previous video. Have a look back at the last video and you'll see that kind of argument at work here. Cot pi plus x is cot x. Cot of 2 pi minus x is minus cot x. Cot of minus x is minus cot x. Secant, similarly again, secant pi minus x is minus secant x. Secant of pi plus x is minus secant x. And again, you could work those out just by taking 1 over cos x and working through the symmetry there. Sec of 2 pi minus x is sec x, and secant of minus x is secant x. Cosec x here, you can see these. If you want to pause the video, write these down and have a look at them. They're your symmetry properties. I suggest you take some time, have a look and work through them, or at least some of them to get a feel for it, but it's just the same way we did it in the last video. Now some trigonometric identities. Well, 1 plus tan squared x is equal to sec squared x, and 1 plus cot squared x is equal to cosec squared x. All right, just some handy identities you might use. Let's have a look a bit at sketching now. So if I go down, all right, step 1, to plot the reciprocal graph of, in this case, cosec x. Okay, first thing you could do is you could plot sin x. Okay, so now if we were just sketching this by hand, same thing would apply, but I'm using a plot here to demonstrate because I'm using a plotting program to do that. Okay, you can see that sin x, the range is from -1 to +1. And when we take the reciprocal of that, then this value here, for instance, here y equals 1, when you take the reciprocal of that, that's going to be 1 as well. Okay, but these values here, as this curve comes down here and approaches y equals 0, as this gets arbitrarily close to y equals 0, the reciprocal of that's going to go off to infinity. So we're expecting a graph to go something like this and similarly this way. Okay, and for each one of those bumps it will do that. However, at y equals 0, pi is equal, at x equals pi, y is equal to 0 here, and so 1 over 0 is infinite, it's undefined, and so we have, that tells you where the asymptotes are as well. So simply plot sin x, then take the reciprocal of everything, and you should be able to sketch cosec x. Okay, step 2 then, draw in the asymptotes. Okay, again, as I just explained there, in the middle here is the plot y equals sin x. Okay, here is the plot at pi on 2. Okay, sine is 1. Okay, the reciprocal of that will be 1 as well. And then as sin x decreases towards 0, cosec x takes off towards infinity. Okay, and again, cosec x is not defined at x equals pi because sin x at pi is 0 and 1 over 0 is undefined. So this is how you're picking out the asymptotes, and that's how you just plot it. Basically, these reciprocal graphs simply sit on top of the basic graph sine or cos x. Okay, let's keep going. Another one here. Okay, okay. If we were going to now transform this, let's say we want a transformed graph. So we wanted cosec of some transformed interval. So if we want to plot, then simply start off with the basic graph. So 3 sine 2 parentheses x minus pi on 4, plotted over this range here. Okay, there we go. There is plotted. Okay, the period there is pi. It's repeating every pi, if you like. You can see that from here. Let's just say pi on 2 to 3 pi on 2. Okay, it's repeating itself every pi. Okay, now to get the reciprocal, same thing again. Okay, you can see wherever this is 0, then you're going to have an asymptote. So at x equals 3 pi on 4, you're going to have an asymptote, pretty simple like that. The only thing, what will happen now is that the reciprocal graph will come in underneath here. So just be careful with that when you take the reciprocal. Okay, because it's you got that 1/3 factor there. You had 3 times here, so 3 sine. And then we take the reciprocal, we get 1/3, a third of that we get down here. That's the only difference. In other words, this transform graph is not sitting on the top here, it's dropped down a bit. Just be aware of that. That's it then.